This video continues our discussion on NMR. In addition to gaining valuable information from the number of signals and the chemical shifts, it is important to also look at integration. Integration is the area under a peak, and it quantifies the relative number of protons giving rise to that signal. This shows an example spectrum where a step curve is measuring the area under each peak. So if we look at these integration values, these are approximately the same, and these are approximately the same. So the signal here and here, those two signals represent the same number of protons, whereas the signals here and here also represent the same number of protons. Now, as the computer operator, you can set one of the signals to a whole number and let it represent a number of protons. So for example, you could set this signal to 1, and then everything else gets adjusted accordingly. So here, this signal also would represent 1, and then this signal would be 1.5 times that of the reference signal. Integrations represent number of protons, so if you have a fraction, you should adjust those values to whole numbers. So here, everything was doubled, which took this value to 2, and this is 2.10, and then these values are approximately 3. Now, what do those integrations represent? They represent relative quantities of protons, and it's important that we use the term relative because they're relative quantities, not absolute quantities. And symmetry can also affect integrations. So for example, if we look at 3-pentanone shown here, it has 2 protons. The protons in blue, all of those blue protons are equivalent to each other, so they give rise to one signal. And then the hydrogens in red. All 6 of those are chemically identical, so they give rise to one signal. So we would have 2 signals. So the relative integration between the blue to red protons would be 2 to 3. Now the absolute count of the protons, you have 4 of the blue protons and 6 of the red protons. And 4 over 6 is the same as a ratio of 2 to 3. To determine the absolute ratio, not just the relative ratio, you need to know the molecular formula. So, for example, if you know the molecular formula for 3-pentanone shown here, then you know that that relative ratio of 2 to 3 really represents absolute ratios of 4 to 6. The final important characteristic is the splitting pattern, also known as multiplicity. This is the number of peaks in a given signal. If it's just one peak, it's called a singlet, 2 a doublet, 3 a triplet, 4 a quartet, 5 a quintet, 6 a sextet, and 7 a septet. And then also, people will often use the term multiplet for things above a quintet. The cause of splitting patterns is due to magnetic effects that protons have on each other. So let's consider protons A and B shown in red and blue. They are color-coded to indicate that they are not chemically equivalent, so they will give rise to different signals. Now, if we're looking from the point of view of HA, the red proton, it is going to be affected by the magnetic field, by the external magnetic field. So for HB, its neighboring proton, HB can be aligned with the field or against the field. This means that there will be 2 different magnetic environments for HA, and as a result, this appears as a doublet. So if HA is in a molecule where HB is aligned against the field, then it experiences a slightly reduced external magnetic field than if HA is in a molecule where HB is aligned with the field. So as a result, HA is experiencing 2 different magnetic environments. Now let's consider the example from the point of view of HA, where it has 2 neighboring protons, HB. So here HB, there's two of them, and they're both blue, so they are chemically equivalent to each other and will give rise to one signal. Now HA will be coupled to both HBs. However, there are three different scenarios that HA could experience. Both of the HB protons could be aligned against the field. One could be aligned with the field and one against, or both could be aligned with the field. So as a result, depending on whether HA is experiencing this scenario, or that scenario, it will experience a slightly different external magnetic field, and therefore it will show up as a triplet. Now notice the height of the triplet is 1 to 2 to 1. This is 1/2 the height of this, and this is 1/2 the height of the middle as well. That's because statistical distribution of these three scenarios is 1 to 2 to 1. Now consider a scenario where HA is split by three neighboring atoms. So what are the different scenarios? All three HBs could be against the field. All three could be aligned with the field. Now, these two in the middle, you could have one with the field and two against, or you could have two with the field and one against. So that means you're going to have a total of 4 different magnetic environments that HA can experience. And as a result, you get 4 peaks, which is the quartet. Now, the height of these peaks is 1 to 3 to 3 to 1. And that's because statistically the distribution is there's one scenario here, 3 different scenarios for the middle ones, and one scenario for all 3 being with the field. So by analyzing the splitting pattern of a signal, you can get information about the number of neighboring equivalent protons on adjacent carbons. And this is where we get the N+1 rule, where the splitting pattern is the number of neighboring equivalent protons plus 1. So in that last example, there were 3 neighboring protons, and we got a quartet. So 3 plus 1 is 4, hence the quartet. There are 3 key rules for splitting. Number 1, equivalent protons cannot split one another because they resonate together. 2, to split each other, protons must be within a 2 or 3 bond distance. So if we look here, splitting is observed between HA and HB. So between HA and HB, there's distance, the distance between them is 2 bonds. Between HA and HB here, it's 1, 2, 3 bonds. So 2 bonds, 3 bonds. Between the HA and the HB here, it's 1, 2, 3, 4 bonds apart. So splitting is generally not observed because those are too far apart. The third key rule is that N+1 rule is very simple, and it only applies to protons that are all equivalent. So the splitting pattern observed for the proton shown in red here will be more complex than a simple triplet because it will be coupled to this proton and to this proton, and these are not equivalent to each other. This would give rise to complex splitting, which I will briefly discuss later. But I will focus primarily on simple splitting. The degree to which a neighboring proton will couple to its neighbor is called the coupling constant, or the J value. And this is the distance between the peaks in a signal, and it's measured in units of hertz. And protons that split each other will have the same coupling constant. So HA couples to HB with the same coupling constant that HB couples to HA with. So if we look at the quartet and the triplet, these coupling constants are all identical. Higher field strength instruments will give better resolution between peaks because the coupling constant is a smaller percentage of the overall hertz available. So the peaks here on the right, that is what you see from a 300 megahertz instrument, whereas the overlapping peaks here are due to a lower field strength instrument being used. There are recognizable splitting patterns that should stand out to you in a spectrum and indicate the presence of certain groups. An ethyl group, for example, will give rise to a quartet and a triplet. The hydrogens in red are coupled to the hydrogens in blue, and they will show up as one signal that's a triplet because the neighboring blue protons, there's 2 of them. So using the 2 plus 1 rule, we place in 2 for N and we get 3. If we look at the signal for the blue protons, they're coupled by the protons in red. And using the N plus 1 rule, we put in a 3 for N. 3 plus 1 is equal to 4. We get a quartet. And the triplet and quartet must have the same coupling constant if they are splitting each other. So if we look at this, you may be tempted to think it's an ethyl group, but notice the spaces between the peaks, they're definitely not the same. So it can't actually be due to an ethyl group where the protons are splitting each other. If you see a singlet with an integration equal to 9, that suggests the presence of a tert-butyl group, because all of those hydrogens in red are chemically equivalent to one another and they aren't coupled to any neighboring protons. An isolated isopropyl group gives a characteristic doublet and septet. So here we see these methyls. So that gives rise to a signal corresponding to all 6 of those blue H's, which are coupled by the one red neighbor. So here we see that as a doublet, but the one red hydrogen, from its perspective, is coupled to the 6 blue hydrogens, and that's going to give a septet, because N plus 1, if N is 6, is going to give us 7 peaks. Complex splitting results when a proton has 2 different kinds of neighbors. So for example, HB here is going to couple to HA, but it's also going to couple to HC. And the complex splitting is not simply going to follow the N plus 1 rule, where N is the total of 5 protons, which are neighboring the HB protons. Instead, you're going to see a quartet of triplets, because first the HB will be split into a quartet by HA, and then HB will be further split into triplets by coupling with HC. And this is called a splitting tree, which is used to determine what the complex splitting patterns will look like. And this is an example where the JAB coupling constant is greater than the JBC coupling constant. Now, if the reverse were true, if JBC was greater than JAB, the signal would appear instead as a triplet of quartets. So in that case, you always are going to split the proton first by the proton that it has the higher coupling constant with. So here, it would first be split by HC into a triplet, and then it would be further split by HA into quartets. And that's how you're getting the triplet of quartet appearance. If JBC is similar to JAB, then the several lines will overlap, and we just call this a multiplet. Splitting is not observed for some protons. For example, the hydrogen on this oxygen. While you might think it would be split into a triplet, it just appears as a singlet. The reason for this is that the hydroxyl proton can be exchanged with trace amounts of acid present in the NMR solvent that's used. And as a result, the exchange blurs the shielding and deshielding effects of the neighboring protons, giving a singlet that is often broadened. We can use proton NMR to distinguish between compounds. So look at these 3 benzene derivatives. It would be very difficult to distinguish these by IR or mass spec. They would all give the same molecular formula, and they would all show the same types of functional groups. However, they are easily distinguished proton NMR because they don't have the same number of protons that give rise to signals. This has 3 signals, the red H's on the methyls, the blue H's, and the yellow H's. This would have 4 signals, and this would have 2 signals. And you can identify this by looking for symmetry. If you're given a formula and a proton NMR spectrum, here are the 5 steps you want to go through. First, calculate the degree of unsaturation. That'll tell you the maximum number of double bonds and or rings that might be present. Then you want to consider the number of signals and integration. That's going to give you clues about the symmetry in the molecule. Then you're going to analyze each signal and draw fragments, and then try to assemble those fragments into a complete structure. And then finally, see if this proposed structure is consistent with all the data you have. Proton NMR can be quite complex because you have to think about the chemical shifts in addition to integration, in addition to splitting patterns, and the number of signals. By contrast, carbon-13 NMR is very simple. And indeed, we really only consider the number of signals and the chemical shift. We're not going to have to worry about splitting and integration. And when we use carbon-13 NMR, it's important to remember that carbon-13 is only 1% of carbon atoms in nature. So we typically need a concentrated NMR sample. And often the running time for taking a carbon NMR is hours and hours, whereas you can get a good proton NMR in a matter of minutes. The reason we don't worry about splitting is that we typically decouple the spectrum. And that's because any carbon-13 hydrogen splitting would be complex, that it would lead to an unreadable spectrum. So when you look at carbon-13 spectra, you're going to see signals that are all singlets. Carbon-13 NMR signals generally appear between 0 and 220 ppm. So there is a much bigger range of frequencies. And each signal represents a unique type of carbon, just like each signal represented a unique type or set of protons. And here again, we want to look at symmetry elements because that can cause carbon atoms to be electronically equivalent, giving rise to one signal. For example, let's look at the symmetry elements in these three. Here we have a plane of symmetry right through the center of the molecule. So everything on the left looks like everything on the right. So this carbon and this carbon are chemically equivalent and would give rise to one signal. This carbon and this carbon would give rise to one signal. This carbon and this carbon would give rise to one signal. And this carbon and this carbon would give rise to one signal. Now, if we look at the next example, we have 5 signals. Again, there's a plane of symmetry right through the center of the molecule. However, notice here that this carbon is not mirrored by the carbon opposite. It's between carbons with 2 methyls, whereas this carbon is not. So those are unique and different from one another. So they each give rise to one signal. These carbons are identical. These carbons are identical. And then finally, the methyl carbons will be identical. So that would give rise to 5 signals. Now this last example, there's 2 planes of symmetry here. One going down this direction and one going down this direction. So as a result, we only get 3 signals here. So these methyl carbons mirror each other, so they are chemically equivalent. These carbons mirror each other. And then all 4 of these carbons are chemically equivalent to one another. They are reflected through this plane and this plane. Just like proton signals, carbon signals are affected by shielding or deshielding. And when we have carbon atoms that are highly deshielded, they show up to the left of the spectrum, downfield between 150 and 220. So for carbonyl carbons, we see them in that range. sp2 hybridized carbon atoms show up in between 100 and 150. sp hybridized atoms as well as sp3 hybridized atoms show up in this range, and then sp3 hybridized carbon atoms that are not deshielded by electronegative atoms show up the furthest upfield. There is an additional type of carbon-13 NMR that you could do called a DEPT, which stands for distortionless enhancement by polarization transfer. And if you do a DEPT 90, only CH signals will appear, carbons attached to one hydrogen. If you would do a depth 135, CH3 and CH signals are positive signals, whereas CH2 signals give negative signals. So for example, if you did a depth 90, you would only get signals for CH, but if you did a depth 135, you would get positive signals for these groups and a negative signal for that group. Now you may not realize it, but many of you may have already experienced an NMR and will work with them in the future. An MRI is essentially just a proton NMR spectrometer. The reason that it's called MRI, that I've always heard, is that people were afraid of nuclear, and so they had to change the wording so that people would actually get MRIs without fear. So in an MRI, different tissues are being analyzed in your body because they have different concentrations of protons, and this is a very mild analysis, so no side effects are experienced. For your end of the video problem, I want you to consider this molecule. And I want you to determine how many proton signals you would see, how many carbon signals you would see, and for the proton signals, what would the splitting pattern be?